Hello, glad to have you again. Alright, so previously we have covered that processors actually needs those resources. You know, you need the main memory, you need the I/O, and you also need the CPU time. And in order to have those, the processors need to send a signal to the OS in order for the OS to understood what needs to be done or what is needed by a process. So for today, we are going to look at the concept of the mutual exclusion. Means that we are going to look at how does concurrent processes being managed and how do these processes communicate with the OS and also with each other. In today's chapter, we are going to look at the concept of concurrency, means that how does actually OS manages those multiple processes going on at the same time inside the system. Previously, we have looked at that the process actually contains information inside their PCB, and this information is actually being monitored using the OS control table. So now we look at the actual definition of concurrency followed by the concept of mutual exclusion, which basically enables the OS to actually manage these processes and for the process to actually work together in order to share those multiple resources. So for today, we are going to look at the concept of concurrency, followed by the concept of mutual exclusion, and how does mutual exclusion is actually being done inside your system. And as always, as a reminder, please take a 5-minute break after you actually watch the video after about 15 to 20 minutes of consumption. So I hope this chapter will benefit you and perhaps raise more interest to the concept of the concurrent processes inside the system. So let's continue. First of all, let's get over with some of the important definition related to concurrency and mutual exclusion. In order to describe the problem of concurrency, we look at this dining philosopher's problem. So in this dining philosopher's problem, if you notice in the diagram, you have 5 philosophers there, and they need to actually finish 5 bowls of spaghetti. And in between them, you can see that there are only 5 forks. So the catch here is, in order for them to actually finish eating the bowl of spaghetti, they need to actually have 2 forks at the same time. So because they only have 5, so each and every one of them have to actually work together and share the use of forks, because sometimes, okay, not all of them can actually eat. So in this case, you can see, okay, let's say this guy here is eating spaghetti, so he will use the fork, okay, and of course this guy cannot use the fork, and then of course this guy can actually use these forks while this guy have to wait, for example. So this scenario, okay, the fork here represent the use of resources, and the spaghetti there represent the use or the instruction that needs to be done or the code that needs to be executed by the program. So in this case, of course, the process here is the philosopher, the code is the spaghetti, and the resource is the forks. So in order to finish the spaghetti, they must work together and of course give way to one another so that every one of those philosophers can eventually finish the bowl of spaghetti. Alright, so remember, the spaghetti is the instruction they need to finish. The philosopher actually signify the process, and the forks actually represent the use of resources. So the problem here is we need to actually find a way for them to actually communicate or signal to one another that perhaps after one person actually finishes using the fork, they can actually give the use of fork to another needed philosopher. So this is the basis program of concurrency, or this is what the problem that needs to be solved in order for processes to finish and for resources to actually be given evenly to the needed process so that they can finish doing all the instruction. Alright, so this is the basis for concurrency program or the concurrency problem, which is the philosopher's problem. So from there, we look at the definition of concurrency. And basically, concurrency means that you have multiple processes, okay, executing simultaneously, and in this condition, they need to actually communicate and interact with one another. Interaction means that, okay, some process is actually doing one thing and one process is actually waiting for something, for example, and during those time, they need to actually communicate and interact in order for the process and also for the OS to understand what is going on and which process has finished, which process is actually waiting for something. So this is where the interaction comes in. So concurrency means that you have multiple processes, and in order for them to finish, they need to interact and communicate so that OS can keep track of what is going on and so that resources can be given evenly between them. Now we look at some of the key terms related to concurrency. So first of all is the concept of atomic operation. So basically atomic operation is that any function or action, okay, that appears to be separated from the process. Okay, it means that this atomic operation actually assists the concurrent process to communicate and actually been given the resources that they want. Okay, do you remember previously what is an example of an atomic operation? Remember the concept of the dispatcher? Okay, so the dispatcher is actually an atomic operation. It exists actually outside the queue of normal processes, and it's there to actually assist the execution of processes and also the assignment of resources to a process that needs those resources. So a dispatcher is an example of atomic operation. So in order to have concurrency, you must have atomic operation that exists outside the queue of those process that is actually waiting to be executed. So that is one concept in concurrency. The first thing is atomic operation. Another important term in concurrency is the concept of critical section. So what is actually a critical section? It simply means that in the line of codes, there is actually a requirement for the use of important resources. So it's basically telling the OS that during the execution, it needs this set of resources for it to actually finish or doing certain instruction. Okay, so each process have a defining line of where or when their critical section is. So this is where it will determine whether the process has to be suspended or perhaps blocked because it is waiting for the use of a shared resources. And of course, shared resources is your main memory, the CPU time, and also the use of I/O devices. So critical section means that in the line of codes, it tells the OS, alright, while doing this instruction, for example, I will need to use these resources for me to actually finish doing this. So that is basically what a critical section is. It tells the OS this process will actually need to use those resources in order for it to finish doing the instruction in its line of codes. And it's also tell the other processes, alright, I will need these resources and please perhaps give me way to actually use these resources because I need to actually finish doing what I need to do. Also, another critical term in concurrency is actually the term deadlock. So what is actually deadlock? Okay, so remember that we have limited resources. Okay, so in this diagram, okay, so let's say there is an error in the scheduling of the giving of resources. So in this scenario, let's say each processes actually possess one critical resources. Okay, so in this example, let's say each of those philosophers, each of them is holding one fork, and they are not actually giving away those fork to give way to other philosopher to it. Okay, so because each of the philosopher needs two forks, remember? So all of them cannot actually do the eating process because all of them are actually waiting for the other fork in order to do the instruction of eating. Okay, and also because there is no enforcement, okay, by the waiter or the dispatcher here, so the processors, or in this case the philosopher, will wait indefinitely and all of them will be deadlocked and eating cannot be continued. So this is the description of deadlock. Means that every process in the cycle is waiting for a resource that's being held by another process. And because the OS doesn't manage this situation very well, and of course, all processes end up being deadlocked and basically your computer hangs because each process cannot actually get the resource that it wants, and at the same time they are not letting go of the resources that are they currently possessing. So that is the definition of deadlock. Aside from deadlock, there is also the concept of lifelock. So what happens in a lifelock? It's basically the same thing. It's just that instead of doing or giving out resources, these processes actually update their condition, but they didn't actually release the resources. So for example, they just update, they are waiting for a resource and they are searching for available resources. But at the same time, they are not releasing what resources that is needed by the other process. Hence, all processes continue to also being stuck. So basically, it's the same as deadlock. No process is actually going down, but what is actually happening is that they are actually updating their status of needing and searching for a resources. In order to fix this problem, another term comes into play. So here we have mutual exclusion. So what is actually mutual exclusion? So mutual exclusion is when those processes can actually work together because they communicate efficiently and they know, okay, let's say they cannot actually execute at that one time, they need to actually release the resources that they are holding. So in this mutual exclusion condition, no two concurrent processes are actually wanting the use of critical resources. It means that, let's say process A, in order to finish, it needs to actually use this memory or CPU time. So at the same time, the other process cannot actually also use the CPU and also the memory that is needed by the other process. So let's say process B is actually holding a set of memory space. It needs to actually release those memory space and give it to the needed process. So this is where process B actually being blocked while process A actually continue to operate. It simply means that processes works together and tolerate their needs with one another. And in order to have this, the OS needs to actually manages the scheduling and the resource management very well in this situation. Okay, so mutual exclusion means that each process understood, okay, if they are not executing, they need to actually release whatever resources that they are currently holding. So this condition prevent the resources being blocked or being held by another process and actually fix the problem of race condition. By having that, so deadlock actually can be prevented because the resources that is not being used or cannot be finished during the cycle of one instruction have to be released and be given to the active or needed processes. So mutual exclusion is a very important concept and condition that you need to actually enforce in order to ensure that all processes eventually can finish. Another condition that could happen in a concurrent process that is executing is, of course, the condition where we have race condition. So what is actually race condition? It simply means that all the resources is actually competing to get the use of the important resources in order for them to actually finish. It means that there is some problem in the scheduling that makes each of the process compete and doesn't want to actually uh, give way to another process to use the critical resources that they need. So this will eventually leads to the occurrence of what we have previously, which is deadlock. There is also an occurrence in concurrency where we have a starvation condition. So this simply means that sometimes there is a bug in the program or in the scheduling, which makes that when you have a program that is supposed to run, but the scheduler or perhaps the dispatcher is overlooking the process. So it eventually doesn't finish at all because its queue or order is being skipped and another process is selected instead of the process that is supposed to run. And eventually, this leads to the condition of starvation, where the process doesn't get the resources that it wants and it doesn't actually finish. So the program just hangs and just doesn't actually execute. So the characteristic in a concurrent process executing at the same time is that, first of all, is the relative speed of execution. So in the concurrent situation, the relative speed is actually depends on, first of all, the activities of other processes. How many instructions that it needs to actually execute, okay, how many resources that it needs, okay, how many cycles until the process finish. And then secondly, is the way the OS handles the interrupt. So this again depends on the OS algorithm. Thirdly, is the scheduling policies of the OS. What type of scheduling policy does it use? So this scheduling policy we will cover specifically in the scheduling chapter. But basically, what you need to remember here is that the speed of the process, whether it finish early or not, finish faster or not, depends on these three characteristics: the activities, the way the OS handles the interrupt, and the scheduling policies that it is being used. So in order for us to be efficiently managing those processes occurring at the same time, these difficulties must be taken care of. First of all is the condition where we have multiple processes requesting the use of global resources, because we have many processes and we have limited resources. So this must be taken care of or managed very well. Secondly, OS needs to be optimally managing the allocation of resources to the process. Again, it's the issue of limited resources and at the same time we have many programs. So it needs to efficiently use whatever information it has in the OS control table together with the information that the process is sharing so that the allocation of resources can be done very well and very efficiently. Third is locating programming error should it happens. Because of course we know that sometimes programmers write certain error in a program. So this will result in some of the uh, wanted result cannot be obtained. So let's say there is an error in calculation that actually result in the process actually in a infinite loop. So the OS must be able to identify this condition and perhaps terminated those unresponsive programs to make way for the other processes. So these three conditions must be handled very well, which is the sharing of global resources, allocating those resources, and also detecting programming error. This is to ensure that process runs smoothly and the allocation of resources can be done very well among processes. So having said that, if let's say in future you are to design your own operating system, this concern must be properly addressed. So first of all, you must to ensure that you must be able to keep track of all the things that happening to all the various program. So it means that you use every information that is there in the OS control table, and also that is being depicted from the process image, what is happening, what is needed from each and individual process. And secondly, you need to actually be able to allocate and deallocate resources for each processes based on condition. So let's say a certain process hangs, then that process must be able to release those resources so that those resources can be used by other processes. Thirdly, you must protect the data and physical resources of each process against interference from other process. So this is where you have process protection or process security. Other processes cannot actually interfere with what's happening with other processes. Okay, so because each process, you remember, is defined by their own process ID, so each allocation of resources must be identified by each individual process that uses them. And only when allocated can those resources be released to the correct processes, and other processes have to wait for their turn. And the fourth one is when you design a scheduler or a process management, you must ensure that the process and outputs are independent of the processing speed, but it must be distributed independently or based on how many process is there occurring at the same time. Because, for example, in the time sharing system, you remember that all the CPU time is divided equally among active processes. So if you have 10 processes, so that CPU time must be given equally to those 10 processes. So it doesn't rely on the speed of the processor, but it relies on how many processes are actually there that is being processed by the CPU. So as future designers of operating system, you must remember these four conditions. So because in a multi-program system, we have concurrent processes competing for the use of shared resources, which is the I/O, the memory, or the CPU time. Hence, this conflict must be well managed by the operating system. So, these problems such as the need for mutual exclusion, the problem of deadlock, and also the problem of possible starvation must be anticipated by the operating system and must be handled very well by the operating system programming and logic. Because we have many processes executing at the same time, now we look at different types of process interaction. First of all is the most normal one, where we have process that is actually unaware of each other. It basically means that each and every process is independent and does not rely to one another's result. For example, I'm opening my web browser and at the same time I'm opening my word processing application. So in this case, let's say I'm opening Chrome and I'm opening Word. Okay, so this is a situation where Word and also Chrome is actually unaware of each other. What they know is that they need to use those shared resources. For example, Word probably needs 10 megabyte of main memory, while Chrome perhaps needs 4 megabyte of main memory. So in this case, they are competing for the use of resources, and their relationship with one another is actually on resource competition. So they are not working together and they are not actually sharing results, but they are competing for the use of resources. So this is very straightforward process interaction, unaware of each other, but they are just competing for the use of resources. Now, the second process interaction is the condition of indirectly aware of each other. Now, for example, previously I'm running Chrome and also I'm running Word. So after that, after a while, let's say I want to actually print whatever I've read or what I've written on my Word and also what I've viewing on Chrome. So from process that is independent, now these two processes are actually indirectly aware of each other because the use of those shared resources. So these shared resources is actually the use of the printer. So now Chrome want to print something and also Word also want to print something. So they are indirectly aware that another process is actually wanting to use the resource, and the other process also aware that another process is also want to use whatever it is want to be using. So this interaction, they are just sharing resources. So they are cooperating because they need to actually give way for one process to actually finish printing, then only they can actually use the printer for their own use. So this is the second condition or second interaction where you have processes that is indirectly aware of each other's existence. The third type of process interaction is where we have a condition where processes are directly aware of each other. So in this scenario, the process is from the very beginning were designed or were written to actually work together and recognize each other data at the same time. So for example, I'm running Excel and I'm running Microsoft Word, and Excel and Word can actually share the data together. Whatever I've written in Word can actually be copied directly to Excel, okay, without actually need to have proper conversion. Because every program in Microsoft Office, Excel for example, we have also Access, we also have Word, were written from the very beginning to work together. So these processes are able to communicate with each other, process ID, very efficiently because they are designed to work together on activities and their codes are compatible with one another. So they immediately can recognize each other. Okay, when they actually interact with one another, they can easily share data and work together because they were written from the very beginning to work together. So this is where we have the condition of process that are directly aware of each other. So this marks the end of part 1. In part 1, we have covered the definition of concurrency and also the concept of mutual exclusion. We have also looked at some of the key terms related to concurrency and what conditions that must be met in order to make sure that process execute very well in a concurrent or multi-programming system. And also we have looked at the process type interaction, which is we have the indirectly, direct, or actually unaware of each other. So take a 5-minute break and then we continue after the break. Alright, so now we continue to the concept of mutual exclusion. What is it? By definition, mutual exclusion means that you are in a condition where no two concurrent processes are actually in the critical section at the same time. Remember what critical section means? It means that no two concurrent processes are actually needs the use of the critical resources at the same time. So it means that each process understood that at one point in time, only one process have the privilege to actually use whatever resources that it wants, and whatever process that is currently holding the resources that the process needs need to let go of that resource for that process that has the priority to use and finish whatever it needs to finish. So this is the concept of mutual exclusion. It is an understanding between process, and it is the way that the OS actually efficiently manage the resource giving and also resource allocation. Hence, from mutual exclusion, each process have an equal chance with the resources and have the possibility for it to finish whatever needs to be done from the beginning until the end. So in order to have mutual exclusion, each and every one of these conditions must be met. So first of all, mutual exclusion must be enforced. What or who is enforcing it? Of course, it is the operating system. So it is the responsibility of the operating system to enforce mutual exclusion. How? It is through perhaps proper scheduling or proper enforcement of resource allocation and resource release. So each and every process must be enforced by the operating system in order to give certain cue or order to the needing process. Secondly, a halted process must not interfere with other process. So for example, when the time comes for a process to stop and given the chance for other process to execute, then it must not actually interfere with the process execution. It means that when a process comes to, for example, a suspended or blocked state, then it must not interfere with other process execution. So in this case, when a process is being blocked, whatever resources is currently being held by the block process must be released and be given to the next process in the queue. So the process or the other process gets a chance to actually execute what it wants, and then it can also give way to other process later on. Thirdly, each process will get a turn eventually if the OS have proper scheduling mechanism and actually manages and uses properly the information that it has in the OS control table. Fourth, a process must be given access to the critical section, means that it must be given access to use whatever it wants, okay? Because if let's say another process is not using that resource, then whenever another process needs to actually use the resource, then it can be given the privilege to use those resources, given the other process is not using it, or the other process is not currently in their critical section to use those resources. Simply put, let's say, okay, we have available resources, another process needs it, then that process can use it. So you don't have to have proper order. But let's say another process is using it, another process also needs to use the resource, then it needs to wait for the correct or its proper queue for it to actually use it. Fifth, there must be no assumption about relative process speed. Okay, depending on how many processes are there, then the process need to actually wait according to the time slice given to it. 6. A process remains in its critical section for a finite time only. It means that each process that is waiting for its turn has a very definite counter. So each process will eventually get its turn because no process can be actually in its critical section for an infinite amount of time. So every process will eventually get a turn. So these are the requirements for mutual exclusion. But the most important thing is that it must be enforced by the operating system. Because this is actual role of the operating system, it needs to actually enforce mutual exclusion to ensure that all process actually gets a turn eventually, and each process actually gets a turn with the resources that it wants in order for the instruction to be executed correctly. So now comes the interesting part. How do we actually have mutual exclusion inside the system? How do we write a program for mutual exclusion in our operating system? So there are a few approaches which we can have for having mutual exclusion. So first of all, we look at the software approach, which is we are going to use semaphores. Secondly, we have the use of hardware approach. We have special machine instruction to indicate the use of resources. And then thirdly, we have programming language support, where you have program to explicitly mention where we have certain condition for certain program to actually arrive to a critical section. So we will look at the approach one by one, the software approach, the hardware approach, and the programming language approach. One thing that you need to remember is that mutual exclusion is a condition where a process can work together and can actually signal when they actually need a resource or when they are actually finished with the use of certain resource based on certain condition. So perhaps when you write a program in the future, alright, so you must remember how to actually make sure that your process can actually communicate. So because there are various ways for a process to communicate, we will look at it one by one, the software approach, hardware approach, and of course, lastly, the programming language approach. Now it's time for you to get to know one of the most important part in mutual exclusion, which is the use of semaphores. So basically, what are semaphores? The fundamental principles in semaphores is that to enable process to communicate and to change state between the availability of resources. Remember in earlier chapter that the process can actually begin from a new state and then perhaps change to a suspend or block state. So how do you suppose that this state changes and who actually tell process to change those state? So simply put, when processes are executing, they are actually waiting to execute certain instruction. And in order to finish certain instruction, they need to use certain resources. So this is where semaphores comes in. Semaphores is actually ways for a process to send signal and also to receive signal to indicate when certain event or certain availability of resources is there for a process to use. So basically, semaphores are special variables used for signaling among processes. Basically, semaphores are variables to enable process to communicate with each other. First of all, we have SEM signal, which enable the transmission of signal between processes. And in order to receive those signals, we have a variable known as SEM weight. And if, let's say, a signal have not yet been transmitted, the process will be suspended until transmission actually takes place. So these are the basic signal in a semaphore. You have the SEM signal to send or transmit data, and you have the SEM weight to actually receive the signal from the other process. So how do we actually use this signal variable in a process execution? So first of all, just like any variable, each of those value must be initialized. So in this case, a SEM weight and SEM signal may be initialized to a non-negative integer value, for example, 0 and above. Secondly, the SEM weight operation decrements the value, and then if the value becomes negative, then the process executing SEM weight is blocked. Else continue. Thirdly, for the SEM signal, each operation of the SEM signal increments back the value. So if the value becomes less than or equals to 0, the process which was blocked by SEM weight previously will become unblocked. Okay, so simply put, let's say SEM weight operation will decrease the value while SEM signal will increase the value. So you have the indicator of the use of resources here. Remember, it begins from 0 and then SEM weight will decrease the value and SEM signal will increase the value. If the value becomes negative, a process will be blocked. If let's say the value becomes positive, the where the process will become unblocked. So do you remember the concept of the change of state between running and block? So how does this process change state? So this is where we see the use of semaphore in determining the change of state between running and block, and then from block to running again, which is to the use of semaphore here. Now, depending on how you design or write a semaphore program, it will determine the type of semaphore that you have. So first of all, if you written a properly queue for your process, then you have a strong semaphore. It simply means that your queue system has a proper way to enable the process that has been blocked the longest to be released from the queue first. So you have the first in, first out order. But if let's say you don't have a proper order in which the process are removed from the queue, then you have a very weak semaphore. So when you run a program, make sure you have a very proper first in, first out order. It means that when a process enter the queue first, it will be released first from the waiting queue. Okay, now we look at how semaphore is used to determine when a process is being blocked and when a process can run. So in this first run, okay, you see that there are four processes. Okay, we have process A, process B, process C, and process D. So in this situation, let's say process A, B, and C depends on the result from process D. And let's say they are actually waiting for a resource from process D. But at the current time, okay, we have the semaphore value as 1, indicate there is still available resources for them to actually use. So in this case, first of all, A is running first. Okay, so when A is running, the value for S is 1. Alright, now take that value first. During the first row here, S value is 1, and then A is executing. Now, what happens after A execute? Right, so after A execute, A issues a SAM wait. So remember what happened when SAM wait is actually operating? So in this case, when SAM wait operation is executed, it will decrease the semaphore value. So in this case, initially S is 1. So when A issues a SAM wait before it enters again into the ready queue, the S value becomes 0. Okay, so take note of that. So previously S is 1. After A execute and then it issues a SAM wait, the value turns to 0. After issues a SAM wait, A enter again into the ready queue. Alright, so next, after A enters the ready queue, it's time for B to execute. Okay, so now currently the value for S is 0. Okay, so what happens after B issues a SAM wait? Of course, it will decrease the semaphore value from 0 to -1. So remember the condition. If the value becomes negative, the process that causes the value to become negative will be blocked. So here, after B issues the SAM wait, the 0 here becomes -1. So here, B actually will be going into the block queue. So next, after B is being blocked, okay, remember the earlier condition that A, B, and C is waiting for a result from D. Okay, so let's say D has finished. Okay, D has finished doing all its actual instruction. So once finished, D will issue a SAM signal. So what happens during a SAM signal? Okay, remember again, SAM signal operation increments the value. Okay, so once the value was -1 because of B SAM wait, now after D finishes, it issues a SAM signal. So SAM signal changes the value from -1 to 0. So because the value is now 0, B, which is currently in a block queue, is released from the block queue and can actually go into the ready queue. Okay, so this is how semaphore is being used. So each time a resources is being used and the process haven't finished, it will issue a SAM wait, which will decrease the semaphore value. But once a process has finished, it will issue a SAM signal indicating that, okay, I have finished, I will release my resources, hence it will increase the semaphore value. So if the semaphore value is 0 and above, then the process that is the furthest or the first in the block queue will be released and be permitted back into the ready queue. So simply put, SAM wait and SAM signal will cause the value of the semaphore to either increase or decrease. This is directly related to signaling whether there is enough resource to use or not. So if the semaphore value is negative, it indicates that there is not enough resources to use. If the value of semaphore is positive, then there is enough resource to use for the next process. So in terms of communicating, SAM wait indicates that a process is still not finished and still needs to use the resource. So when a process initiates a SAM wait and it causes the semaphore value to become negative, then the process that causes the value of semaphore to become negative will be blocked. Okay, it simply indicates that I need the resources again, but resources is not enough, hence I need to be blocked. On the other hand, if a process issues a SAM signal, it simply means that, alright, I have finished, I will not need to use this resource, so I will return back this resource. So this will cause the semaphore value to increase. So when enough increase in value of the semaphore until the semaphore becomes 0 or more, then the previously blocked process will be released. It simply means that, okay, you have enough resource to use, so because you are waiting previously for this resource to be available, now it's time for you to be running next. So in a nutshell, SAM wait is to indicate, okay, I will need the resource, but perhaps the resource is not available, and SAM signal means that I have finished, I will return this portion of the resource that I have used. So that's why SAM wait decreases the value, SAM signal increases back the value. It is just a way for indication for the resource availability. If the value is negative, then there is not enough resource. If the value is positive again, then there will be enough resource for process to use. So in order to properly implement the use of semaphore, you can either have it as an atomic process or in atomic primitive. It means that the value is standalone and independent of the other process value. So it's just there to indicate the value or the indication of resource availability. And this value can be referred back to any process that will need to use that resource. Secondly, it can either be implemented as hardware or firmware algorithm. Hardware or firmware means that it can be used as a counter for resource availability. And then if you want to read further on this use of semaphore, you can try and Google the Dekkers or Peterson's algorithm for semaphore. Thirdly, you can also have the assistance of hardware-supported scheme for mutual exclusion. It means that aside from just writing the program to increase and decrease the value of semaphore, you can also add the functionality of hardware-supported scheme, meaning that perhaps you can have hardware signal to send those indication of resource availability. But, okay, simply put, you just have to remember that semaphore is being used as indicator of resource availability. So if there is not enough resource, a process needs to be blocked. If there is enough resource, then process can execute. That is the very core of why semaphore is being used and how does process communicate how much resource did they need for each and every cycle during their execution. So we come to the end of chapter 5, part 1. So I hope you can recap back on what we have learned today on the concept of concurrency, what are the conditions and why do we have concurrency and mutual exclusion in order to make sure that process can actually finish whatever it wants to finish and whenever it wants to use a set of resources for it to actually finish what it needs to be finished. And then we need to also remember the role of semaphore in having mutual exclusion or mutual exclusivity to the use of resources. What value actually increase the value of semaphore and what value actually decrease the value of semaphore? And why does this value need to constantly be decreased and increased? What does it signify? Okay, so I hope you can go back to this concept, study again, and if you have any question, feel free to ask me. Okay, but the most important thing for this part is for you to understand the role of semaphore in actually assisting the OS to enable having mutual exclusivity and concurrent process can actually execute at the same time inside your computer. So I hope it has been beneficial and I see you again in the next session. Thank you very much.